Today let's take a look at a really cool relationship between graph theory and the golden ratio. To begin, we're going to need the concept of the simplex graph operation. I covered this in an earlier video if you're interested in learning more about it, but I'll do a quick recap here. The simplex graph of a graph G, which we'll write as K of G, is itself a graph with one vertex for each click in G, and in which two vertices are adjacent when their corresponding clicks differ by the presence of a single vertex. Note that if we have a vertex V in the simplex graph that corresponds to a click of size n in G, then V can only be adjacent to vertices corresponding to clicks of size n plus 1 or n minus 1 in G. We can also iterate this operation. The second simplex of a graph is the simplex of that graph. The third simplex is the simplex of the second simplex, and so on. In this video, we'll use exponent notation to denote repeated simplex graphs. Now comes the fun part. What does the ratio of the number of edges, also known as a graph's size, to the number of vertices, also known as a graph's order, tend to as we iterate this operation? That is, let's take the first simplex, second simplex, third simplex, and so on, and look at the ratio of the size to the order of each graph. Amazingly, it doesn't matter what graph you start with, the limit of this ratio as we continue to iterate the simplex graph operation exists and will always be the golden ratio, 1 plus root 5 all over 2. Why is this true? Well, first, it would be nice to have some kind of formula for the number of vertices and for the number of edges in, say, the nth simplex of some graph. To find a formula, first, let's look at what taking the first simplex does. It gives us a graph where the largest click is at most a 2-click. This is because of the rules of a simplex graph. Simplex graph vertices corresponding to n clicks in the original graph can only be adjacent to simplex graph vertices corresponding to n plus 1 or n minus 1 clicks in the original graph. Why does this rule mean that the largest click in a first simplex of a graph is at most a 2-click? Well, suppose that a 3-click existed in the first simplex of some graph. Then there are 3 mutually adjacent vertices u, v, and w in this simplex graph. Now let n be the number of vertices in the click corresponding to u in the original graph. Then the click corresponding to vertex v has either n plus 1 or n minus 1 vertices, and the same goes for the click corresponding to vertex w. However, vertices v and w are also adjacent. As we know, that means their corresponding clicks must differ in size by 1. Yet that's impossible because either they're both n plus 1 clicks, both n minus 1 clicks, or one is an n plus 1 click and another is an n minus 1 click. Regardless, they differ by only 0 or 2 vertices, contradicting the fact that they are adjacent. And so there cannot be a 3-click in a simplex graph. Since all higher clicks would have to include a 3-click, the largest possible click in a simplex graph is a 2-click, which is just an edge between two vertices whose corresponding clicks in the original graph differ by the presence of a single vertex. This fact helps us to make a formula for the number of vertices and edges in iterated simplex graphs. Observe that if we take the simplex of a simplex graph, we would have as many vertices as there are clicks in the first simplex graph. So how many clicks are in the first simplex graph? Since its largest click is at most a 2-click, then that would be the number of 2 clicks plus the number of 1 clicks plus the number of empty clicks. This is just the sum of the number of edges, the number of vertices, and 1. That's how many clicks are in the first simplex graph. So that's how many vertices are in the second simplex graph. If we let v sub n be the number of vertices in the nth simplex graph, and e sub n be the number of edges in the nth simplex graph, then what we've just found is that v sub 2 equals v sub 1 plus e sub 1 plus 1. And remember, the second simplex graph has the same property as the first. Its highest click is a 2-click, meaning that the number of vertices in the third simplex graph is v sub 2 plus e sub 2 plus 1. Do you see the pattern? We have a recursive formula for the number of vertices in the nth simplex graph. V sub n equals v sub n minus 1 plus e sub n minus 1 plus 1 for n greater than or equal to 2. To use this formula, we need some way to calculate the number of edges in the nth simplex graph. For this, I'd like to rethink how we see the simplex graph operation. When we operate on a graph that has a highest click of size 2 or smaller, the simplex graph can be thought of like this. Replace each edge E with a vertex v sub E adjacent to the endpoints of that edge, and then add another vertex v sub 0 that is adjacent to every original vertex in the graph. Note that the number of edges in this graph is the double of the number of edges in the previous graph plus the number of vertices in the previous graph. With this new perspective, we see that the number of edges in the simplex of a simplex graph is always the sum of twice the number of edges in the previous simplex graph with the number of vertices in the previous simplex graph. Alright, we have two recursive formulas we can work with now. Starting with just the number of vertices and edges in the first simplex of a graph, we can use each of these formulas to calculate the number of vertices and edges in the second simplex of a graph, and continue in this way. But it would be nice to have a formula for the number of vertices that depends only upon the number of vertices in the previous simplex graphs. And it'd be nice to have a formula for the number of edges that depends only upon the number of edges in the previous simplex graphs. That way we can use the theory of linear recurrences to solve for a continuous function that gives us the number of vertices or edges in the nth simplex graph, which we can then use to examine limiting behavior and hopefully find that the limit as n goes to infinity of the ratio between the number of edges and vertices is the golden ratio. Let's start by trying to find a number of edges formula that only depends upon the number of edges in the previous simplex graphs. For n greater than or equal to 2, we have these two formulas. Okay, now let's give ourselves some room to work with and let n be greater than or equal to 3. Now the equations in blue are also true. Next, let's subtract the equation on the right from the one on the left to get the following. Now get the v sub n minus 1 to one side. We have v sub n minus 1 written all in terms of e's now. And remember our formula for e sub n. Let's substitute what we just found for v sub n minus 1 into the formula for e sub n. Simplifying, what we get is that e sub n equals 3 e sub n minus 1 minus e sub n minus 2 plus 1 for n greater than or equal to 3. Neat, that's a formula that only depends on the number of edges in previous simplex graphs. Now let's try and get a similar result for the vertex formula. In our formula for v sub n, let's plug in the formula for v sub n minus 1 and the formula for e sub n minus 1 that we have in the blue box. Simplifying, we have this. Now let's do a little trick here. Let's add and subtract v sub n minus 2 from the right side. Now let's add and subtract 1 from the right side. And now factor out a 3 to get this. That term by the 3 is exactly v sub n minus 1. So let's substitute v sub n minus 1 for it in our equation. what we get is that v sub n equals 3v sub n minus 1 minus v sub n minus 2 minus 1. We can now solve each of these linear recurrences for a continuous function that gives us the number of vertices and edges in a simplex graph, which will let us analyze the limiting behavior of the ratio of these sequences. As an exercise, I encourage you to pause the video and find the general form solution for the recurrence v sub n without solving for the arbitrary constants. We'll do that together. At the top of the screen, you can see the general form solution to v sub n. All we need to do now is solve for the arbitrary constants c sub 1 and c sub 2, using initial values v sub 0 for the number of vertices in the first simplex graph and v sub 1 for the number of vertices in the second simplex graph. Plugging in n equals 0 to our formula gives us this, which we can simplify to c sub 1 equals v sub 0 minus c sub 2 minus 1. And then plugging in 1 to our formula gives us this equation. And then we can substitute v sub 0 minus c sub 2 minus 1 for c sub 1 in the equation in our second line. And then we can simplify. Now we have c sub 2 written in terms of v sub 0 and v sub 1, which automatically gives us c sub 1 written in terms of v sub 0 and v sub 1. Finally, we can pull out a negative and make our arbitrary constants look a little nicer. Alright, let's substitute what we found for c sub 1 and c sub 2. This is our solution written in terms of the sizes of the vertex sets of the first and second simplex graphs of any graph. Now remember, in this sequence, the 0 index corresponds to the first simplex graph. We can shift the exponent to n minus 1 now, because it'd be nice for index 1 to correspond to the first simplex graph. This is our result. As an example, let's use the values for the number of vertices and edges in an actual graph. Let's use this graph. It has the following first and second simplex graphs. Now substitute the number of vertices in those simplex graphs into our formula. The resulting function gives us the number of vertices of the nth simplex of this graph. Here's what this function looks like when plotted. The y value taken at each positive integer x value is the size of some simplex of our graph. Moving on, we still don't have a solution for the edge recurrence. I encourage you to pause the video and find the general form solution for this recurrence. Alright, at the top of the screen we have our general form solution. We can use the same process as before to solve for the arbitrary constants in terms of e sub 0 and e sub 1. And again, we can pull out a negative to make these arbitrary constants look a little nicer. This is what it comes out to be. And shifting, so our index 1 corresponds to the size of the first simplex graph, we get this. Now let's pull up the recurrence for the number of vertices in a simplex graph alongside it. Interestingly, the ratio of these coefficients of the first terms in each formula is the golden ratio. It takes some work to show this, so I challenge you to first verify this for yourself using our initial two recurrences and playing around with the expressions we have for our two constants. Here's the verification. We're going to take the coefficient in yellow and substitute 2 times e sub 1 plus v sub 1 for e sub 2. Then we're going to take the coefficient in pink and substitute v sub 1 plus e sub 1 plus 1 for v sub 2. Now if you multiply the golden ratio by the number in the purple box, you get the number in the yellow box. Isn't that neat? Now that we know the coefficient of the first term in our function for the number of edges is the golden ratio times that first coefficient in the function for the number of vertices, it follows that the limit as n goes to infinity of the ratio of these two sequences exists and is the golden ratio. Intuitively, this is because in the first term of both formulas, we have the same number that is greater than 1 raised to a variable power, while in the second term of both formulas, we have the same number whose magnitude is less than 1 raised to a variable power. As we let this variable power become arbitrarily large, meaning we iterate the simplex graph operation over and over, the second and third terms in both formulas will become very small in comparison to the first terms. So the fraction e sub n over v sub n will tend towards the ratio of the coefficients of the first terms, which as we covered earlier is the golden ratio, 1 plus root 5 all over 2. As a challenge, feel free to pause the video now and prove rigorously that the limit as n goes to infinity of e sub n over v sub n exists and is equal to the golden ratio. Isn't it amazing that the ratio of the number of edges to the number of vertices in iterated simplex graphs approaches the golden ratio, regardless of the graph we start with? As a final example, if we take the graph in our previous example and find the number of edges and the number of vertices in the first 9 simplex graphs, and find their ratios, we already obtain a number somewhat close to the golden ratio. And if we jump to the 20th simplex graph, we have a number that's correct to 7 decimal places. That's it for this video. In future videos, we'll take a look at some neat graph polynomials, percolation centrality, and explore some graph products in greater depth. Thanks for watching. Please subscribe, like, share, and comment if you liked the video. Have a great day.